So in today's lesson, we're going to be talking about exponential functions. So it's really another nonlinear function. And we've talked about other nonlinear functions like absolute value, or say something like this, a piecewise function, or perhaps step function. Right, so we've seen nonlinear functions before. This is going to be the first one where we're not using rigid straight lines. That's going to be a big difference. So let's go ahead and let's start taking a look here. A function in the form y equals ab to the x is an exponential function. Exponential functions are not linear. Linear functions have a constant difference. Like, remember when we were talking about, for example, arithmetic sequences. Arithmetic sequences had that common difference that we were looking for. In exponential functions, we are looking for a constant factor. All right, and we'll explore that looking at tables and looking at graphs. So first off, let's look at a here. And what I'm looking for is, does a represent linear or exponential function? So our x values are increasing 0 to 1, 1 to 2, 2 to 3. Nothing too fancy there. Our y values are increasing 2 to 4, so that's a common difference of 2. 4 to 6, looks like that is continuing, plus 2. And 6 to 8, again continuing, plus 2. So what we have here is in fact linear. It's a lot like an arithmetic sequence. It's showing a linear relationship. Now let's come over to b. X values again are going 0 to 1, 1 to 2, 2 to 3. Nothing very fun. When I look at the y's though, I start at 4 and I move to 8. Okay, plus 4. I go from 8 to 16. Okay, interesting. That's a jump of 8. And I go from 16 to 32. That's a jump of 16. So there's obviously not that common difference between them all. But let's see if perhaps something else is going on. What's another way that I could go from 4 to 8? Well, I could multiply by 2. Is that the same common constant factor going from 8 to 16? Yeah, I multiply by 2. And from 16 to 32, again, I multiply by 2. This is showing an exponential function. Do me a favor, try C and D on your own. We will look into those and check in class. When you have done C and D, we can now move on to example 2. Example 2 is we're basically taking an exponential function, right? Exponential functions are written in the form y equals ab raised to the x. So that's what we have here, y equals negative 2 times 5 raised to the x. And what we're going to do is just substitute in and say x equals 3. Easy enough. We've had tons of opportunities to substitute x values into an equation. All right, so let's go. Let's rewrite y equals negative 2 times 5 raised to the x, where x is 3. Okay, so all I've done here is substitute the x into the equation. Now I can evaluate. Y equals negative 2 times 5 to the third power, which we've seen a couple times, 125. Now y equals negative 2 times 125. Well, 2 times 125 is 250. Negative 250. Solved. Now let's head over to b. b is going to be the exact same process. I'm going to be substituting into this exponential equation an x of negative 2. So I'm going to rewrite. Let me change color here. And say y equals 3 times, you know what, I'm going to write 1/2. I like fractions better than decimals. And I'm going to substitute the x as negative 2. Okay, so hopefully I didn't throw you off there. I just changed 0.5 to 1/2, and then I did the substitution of x to be -2. So now I have to evaluate y equals 3 times 1/2 to the -2nd. Now negative exponents require me to flip the base. Okay, this is a 1/2, so that means that I have to take the reciprocal of it, 2, and raise that number to the positive exponent. Okay, in class and mostly we've been dealing with when it says something like 5 to the -2, and it's a whole number. I take the reciprocal, 1/5, and then I can raise that to the positive. This way, it's the exact same thing, we're just going from the fraction to the whole number this time. Alright, so try not to get too confused by that part. So now we need to evaluate y equals 3 times 2 squared. 2 squared is 4. So what does y equal? 12. Fantastic. Again, try C and D on your own. We will check in on those in class, and then we will move on. Alright, once you have done C and D from example 2, we can come into example 3 here. Now example 3, we're doing something very different. We're not looking at a table, we're not substituting values. We're actually going to look at what this thing looks like when it's plotted on an XY graph. So the first way that we learned how to graph linear functions was to make a table. Make a table of values, plot the points, draw a line through. So we're going to do the exact same thing in this case. Okay? I have a table somewhat set up here. I've chosen some x values somewhere around, the origin. That's generally a good place to start. It's where most of the action happens. So I'm going to take my equation that I'm looking at, y equals 2 to the x, which again is an exponential function, and I'm going to start substituting these x values in. I'm going to substitute them in, see what the output y is. So -2 going into this equation gives me y equals 2 raised to the -2. Well, like we just said on the last one, a negative exponent requires me to take the reciprocal of the base. So 1/2 raised to the positive exponent 2. What does that get me? 1/4. My next one, y equals 2 to the -1, again still requires me to take the reciprocal, 1/2. And this time I can raise it to the positive exponent 1. So that gives me a 1/2. When I put in a 0, anything raised to the 0 power, including 2, equals 1. My next one, 2 to the first, anything to the first power equals itself. So that's just going to give me a 2. And my next one, 2 squared, is 4. 2 cubed is 8. Fantastic. So now I need to actually plot these. I'm going to come over here to the origin. This is where I'm going to start off. I move -2 on the x, 1, 2, and I go up 1/4, and I put a little point there. My next plot is -1, 1/2, so I go -1 and up to 1/2. My third is 0, 1, plot it right there. And so far this looks like a linear equation. It doesn't look very different. But I'm going to keep going, trust in the fact that it's not supposed to be linear. So let's see what it looks like. 1 and up to 2. Okay, now things are starting to change a little bit. It seems like I'm going in a curve here. Now my next one's going to be 2 and then up 1, 2, 3, 4. Okay, now it's definitely curving up. And my last one, 3 and 8. Alright. So, I obviously have this, upward turn going on here. So what I'm going to try and do, I'm going to try and draw as smooth of a curve as I can that travels through all of these points. Obviously it's not perfect, but I tried. So what do we see going on here? Because graph y equals 2 raised to the x power was only half of what I'm supposed to be doing here in example 3. I also have to describe its domain and its range. Alright, now I know that this has been a bit of a struggle for us, but let's try and work through it. Domain. domain is talking about x values. Range. Range is talking about y values. So let's focus on domain first. X values are the values that travel left and right. So how does the graph behave left and right? If I go to increasingly smaller values of x, like as I go more and more negative to the left here, what happens to the graph? It continues. So yes, from 0 and going increasingly negative, the graph continues. As I go from 0 to more increasingly positive values of x, what happens to the graph? It continues. It covers every single value moving from 0 to all positive numbers. So for this domain, I can literally say it consists of all real numbers. Now what about the range? Is the range the same way? If I again start at the origin and start looking at increasing y values, does it go on forever? Does it look like this graph is going to cover all of these y values from 0 and on? Yeah, it does. What about going in the other direction, from 0 and down? Does it look like this graph is going to cover them? No, actually. It doesn't look like the graph covers anything below 0. In fact, it looks like it almost kind of levels out going this way, so it never will cross 0. Okay, so what I'm looking at here is a range that describes only the positive real values, only things like 1, 2, 3, 4, not things like negative 1, 2, 3, 4. So only all positives. Why don't you try part B, and we'll take a look at that in class. Alright, so you can do all of your work here for B, and then continue on to try C. Feel free to pause the video at any time so that you can stop and take a look as well. Once you've worked with B and C and you've gone through them and you feel confident with it, I want to look at example 5, and I want to look at a real-life situation. Okay? Now, what we have going on here is a representation of bacteria population after so much time has passed. So in the graph, we have so much time that's passing on the x-axis, and we have population of bacteria in the y. Okay, so a lot of times in biology or chemistry or sciences, we can model things that happen in nature with exponential or something we might talk about later, logarithmic functions. So let's see. Write an exponential function that represents the population. Okay. First of all, that might seem crazy daunting. Right at first, but I think that we can do it. Okay? First, what we need to do is figure out what's happening here. I have some x's, I have some y's. What type of common factor are we looking at? Well, my x's go 0, they go 1, 2, 3, and 4. And the y's that correspond to them are 0, 3, 1, 12, 2, 48, 3, 192, and 4, 768. Okay, now over here these numbers are starting to get bigger, so let's look down at the bottom. Is there some sort of common factor that you're seeing here to get from 3 to 12, from 12 to 48? Yeah, you're multiplying by 4 each time. 3 to 12, multiply by 4. 12 to 48, multiply by 4. 48 to 192, multiply by 4. 192 to 768, yeah, you're multiplying by 4. Alright, so we've got our common factor. What else do we need? The y-intercept. What is the y-intercept? Well, what do we know about y-intercept? The y-intercept is where x equals 0. Right here. 0, 3 is our y-intercept. So if we look at the form y equals ab raised to the x, we have all of the information we need. Y equals the y-intercept 3 times the common factor 4 raised to the x. This is all that we need to create our function. Now let's take a look at what we can do with this function. The last thing we're going to do is find the population after 12 hours and also after 5 days. So this is two different problems in one. One of them is going to take our equation and substitute a specific x value. The other one is going to take an equation and again substitute a different x value. So in our first one, we need to think, what is the units that we're using for x? Was it hours? Was it minutes? Was it seconds? I don't quite remember. So we have to come back. Let's take a look. We were using population versus time in days. That's very important to how our x is visualized. So let's go over back to our problem. And if I need to represent 12 hours given an x value, and x is in days, how many days is 12 hours? Well, if one day consists of 24 hours, 12 hours is 1/2. Now what about in our second example? I need to represent 5 days. X is supposed to be in days, so that one's easy. That's just a 5. And now it's a matter of evaluating. Okay, if you were okay doing example 2, this shouldn't be too difficult. Y equals 3 times 4 raised to the 1/2. What is 4 raised to the 1/2? Well, we talked about fractional exponents, especially ones with a numerator of 1. This implies the square root. So y equals 3 times the square root of 4, which is 2. Y equals 6. Fantastic. Now let's look at the other one. Y equals 3 times 4 raised to the 5th. Alright, 4 raised to the 5th. That one you might not know right off the top of your head. So you may need to use a calculator or just go off to the side and multiply 4 out 5 times. But what you're going to get would be 1024. Oops. That's 1024. Now 3 times 1024, that might be a little bit easier. What you should get is 3072. So what this tells me is that after 12 hours, I have 6 bacteria. After 5 days, I have 3072. Feel free to watch this video as many times as you need to, and work on any other problems that you'd like to from the text. If you have any issues, we will be going over it again in class.